Thank you all for coming. I have sort of two stories I want to tell you tonight. One is about how we get to ultra-cold temperatures, and even sort of what we mean by that. So we're going to talk about chemical reactions that happen at temperatures like a couple hundred nanokelvins to a couple of microkelvins, so millionths or even billionths of a degree above absolute zero. So first I want to kind of give you a brief idea of how we get there, and then I want to tell you one of the very sort of exciting things we see when we look at chemistry in this temperature regime. But to get started, maybe let me just set a couple of scales here. So I'm going to talk about atoms and molecules. Atoms look like that. Not really. Kind of like that. Close enough. So the question is, how big are they? Okay. The answer is tiny. Okay, that's not terribly helpful. I like to sort of make a bit of a comparison here. If you look 10 million times bigger than an atom, you're looking at a grain of sand. Okay? So roughly speaking, sand comes in different sizes and shapes. It's all good. But roughly speaking, there's like 10 million atoms across the diameter of a grain of sand. Okay? So an atom is to a grain of sand as, what would you guess, is 10 million times bigger than a grain of sand? Not quite. That would be extraordinarily big. But it's big. It's a mountain. This is a good mountain. It's a big volcano. Okay? So an atom is to a grain of sand the way that a grain of sand is to a large mountain. This is not just like a little mountain. This is a big guy. Okay? So that's the size scale we're thinking about when we talk about atoms and molecules. Okay? And then we're going to talk about them at ultra-cold temperatures. And to really get at what ultra-cold means, a normal thermometer just won't do. I like to use a logarithmic thermometer. So on our logarithmic thermometer here, there's room temperature, 300 Kelvin. Okay? The surface of the sun, just a little above that, okay, 6,000 Kelvin. Not that far, really, in the grand scheme of things. Okay, go to the core of the sun, a star exploding, billionths of a second after the beginning of the universe. That's the kind of distance we're looking at. If you go the same distance in the opposite direction, you get to where we are when we do these experiments. Okay? So when we talk about going ultra cold, we really mean sort of almost as cold as one can imagine. Okay? We're going to a place where the motion of atoms stops at least as far as it can stop quantum mechanically. Okay? If you know anything about the uncertainty principle, you can't ever have exactly zero. But boy, we get as close as you can without breaking quantum mechanics. So this work is here in that little yellow rectangle. So how we get there is we use these big hot lasers that burn through steel. Okay, this is the kind of laser that we use in some of our experiments, doing what it was originally designed for, which is cutting sheet metal in a factory. But it turns out if you take that same laser, focus it super tightly into a vacuum chamber, these atoms feel it as like a nice gentle bowl. They just kind of hang out in there. They're not catching fire, burning. We'd have problems with the safety office that they did. Turns out these hot lasers can make our atoms extremely cold. And I want to talk you through how that happens. There's sort of three big ideas you need to get from where our experiments start, which is actually hotter than room temperature, all the way down to nanokelvins. And the first big idea you need to understand this is resonance. Okay? So resonance is why most musical instruments work. Okay? If you think about what's inside of a piano, they're the strings, that's the stuff that makes the note, and there's a hammer. The hammer just whacks stuff, right? There's nothing subtle about a hammer. A hammer is making noise. And what do we mean by noise? Okay, it's the music I listen to, my mother, her opinion of it. It's a sound that's got a lot of different frequencies in it, okay? When you hit with the hammer, you're exciting all these different frequencies, but the string has a resonance. It grabs one frequency and rings out at that frequency, and that's what you hear out in the concert hall, right? If you just heard wham, 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 you wouldn't be going to listen to Beethoven's piano concerto, right? So that resonance that you maybe know from musical instruments, we also get these in atoms. And in atoms, those resonances correspond to frequencies of light. Okay? So if you're, let's say, my age or older, you might recognize that bright yellow-orange color. It's a sodium vapor street lamp. Okay? So there's a little gas of sodium atoms inside there, and there's a spark. And the spark is like the electronic equivalent of a hammer. Lots of different frequencies in that spark. One of them corresponds to this sort of yellow-orange color. And the sodium atoms, we'll say, ring out. They absorb that energy and they re-emit it as light. Okay? So that's sodium, the blue is mercury. Every element has its own little fingerprint of what its resonances are. Now, this is as complicated of a picture of an atom as we will need tonight. It's in fact way simpler than the real deal, but that's fine because it captures what we need to know, which is electrons sit outside of the nucleus. They have stable, let's call them orbitals, why not? Okay? And there are very specific energy differences between these orbitals. Okay? So if I send in a spark, some kind of broadband excitation, an excitation with lots of different frequencies, okay? Only one of those frequencies corresponds to the energy difference between the two levels of the atom. So that one will get absorbed, and all the rest just pass right through. The atom doesn't notice it. Okay? That atom is now in an excited state. It's absorbed some energy, and that's unstable. Sometime later, it's going to re-emit that energy as a particle of light with exactly the same frequency as what it absorbed. So that's what we mean by resonance. There are very specific frequencies of light, and for frequency, you can think this is like the color of the light, except atoms can see colors way more precisely than you can. In my lab, we'll make 5, 6, 8 different frequencies of red light that all look very red to me, but the lithium atoms can tell the difference. I said this is the most complicated picture we'll need, and it's more complicated than we need from here on out. All we need to know is that an atom can be in its ground state, that's its lowest energy, that's how it wants to hang out in life, and it can be in one particular excited state. Now, atoms actually have a ton of different excited states. As long as we're using a laser that has a very specific color, we only care about one excited state. We'll talk to the one excited state and no others. So that's our whole picture of an atom. Ground, excited, done. We want to slow these things down. Okay? Now, the way that this works, if we know what direction the atoms are moving, we can shine light in the opposite direction. And if the light is resonant to the atoms, they'll absorb it, re-emit it in a random direction, absorb it again, absorb it again. Every time they absorb some of that light, they're getting a little kick backwards. Okay? So if we send the light, one photon gets scattered. Those gray lines are the little kicks that the atom gets. Every time it scatters, there's one kick in a random direction and one that away. Nope, that away. That's going to slow the atom down. Okay? As long as we know what direction it's going, we can shine resonant light, it'll scatter it, we can slow it down. Now, we have to know what direction it's going. We don't necessarily know that. Okay? So resonance was the first idea. Doppler versus Zeeman. This is the second idea. This is how we deal with the fact that we may not know which direction they're going. Okay? So the Doppler shift you know, even if you don't know the name. Race car goes by, right? The frequency that it's emitting is shifted upward when it's coming toward you and downward when it goes away. Okay? That's true of sound waves. It's also true of light waves. Now, when the car is driving toward you, it doesn't look blue and then look red when it drives away. I mean, it does, but again, at a level that you'll never notice. Okay? But the atoms can tell colors way better than we can. The atoms can see the difference between light that's coming toward them versus light that's moving away from them. Okay? So to start our ultracold experiments, we heat things up. Okay? We do not have an open flame in the lab, just clarity. But we do have a chunk of lithium metal sitting in an oven. The oven's got a little hole in the front, and the atoms come shooting out of the hole in the front. Okay? So to start with, we know what direction they're going. Okay? Now, this is showing you that when they come out of the oven, they're all hot. There's a huge distribution of speeds. Okay? And we'd like to slow them all down. But, as I said, they see very specific colors. And so if we shine a laser with one frequency in there, one specific speed will say, oh, that looks resonant. For the atoms down here, the frequency won't look high enough. For the atoms here, the frequency looks too high. These guys right here, they start scattering the light. They say, oh, that's resonant. That's great. I'm slowing down. Oh, I slowed down too much. Now the light doesn't look resonant anymore. So that Doppler shift is sort of great because we can address one particular velocity. But we don't want to address just one particular velocity. We want to talk to all of them. We want to slow them all down. So the trade-off comes when we add in something called a Zeeman shift. Now, a Zeeman shift has to do with how atoms interact with magnetic fields. Okay? And in that picture that was almost right, but not quite, of sort of electrons whirling around in an atom, they're little charges which make little currents, and so they interact with magnetic fields. Okay? There's more to it than that, but that's the basic idea. That magnetic field is going to change the distance between ground and excited. Okay? If we turn up the magnetic field, they get closer together. Now that turns out that's great. Okay? We're going to shine some light, and we're going to have a magnetic field. The magnetic field sweeps up in magnitude as we get further from the oven. And what that accomplishes for us is the distance between ground and excited shrinks, which means we don't need quite as high a frequency of light. And that's good, because as the atoms are slowing down, they see a lower frequency. Right? That's what the Doppler shift is doing for us. As the atoms slow down, they see a lower frequency, and with the magnetic field, we say, hey, you should see that as resonant anyway, even though it's lower. Okay? So we take the Doppler shift that allows us to control particular velocity, we add a magnetic field that lets us talk to different velocities in different places, and when we put it all together, we can slow the atoms down. So this was without a magnetic field, we're stalled, but as we go down, now all of a sudden, these are on resonance, and then these are on resonance, and these are on resonance. We're piling them up. Okay? We keep going, we keep piling up a bigger and bigger pile of these slowed atoms. They get to that chamber where we want to do experiments, and we've got a huge pile of very slow atoms, and some stragglers we leave behind. Not everyone can scatter at the right rate, life is like that. When we do it in the lab, it looks like that. Okay? So for like 10 years, I've been meaning to change the colors on this. So the yellow that's washed out just enough to almost look like the orange, that's the velocity distribution that I showed you at the beginning, right? This big, broad hump. There's atoms at a lot of different velocities. And when we turn on that slowing beam, it scoops up a whole bunch of them, piles them up at a velocity that you didn't even see atoms at before. There's very few of them down at zero velocity, but we pile up a huge number of them so that we can catch them. Now, once we've slowed them all down and we're ready to catch them, we just do the same thing, but from all 6 directions. So by making a little conspiracy of magnetic fields and Doppler shifts, we can grab atoms, slow them down, keep them in one spot, and cool them. We can cool them. This is a nice one. It's a little red football here. Sorry, American rules football, not a soccer ball. That's a cloud of 100 million dysprosium atoms at about 20 microkelvins. Okay? They're scattering light, which is why you can see them. Atoms are much too small to see an individual one with your eye, but you can see the light that they're scattering away. The fact that they're glowing means they're scattering light. And in the end, that puts a limit on how cold we can get them. I know this cloud is 20 microkelvins because we can't get much colder than that if they're still scattering light. It's pretty good. It's pretty cold. It's not ultra cold. Well, some people call it ultra cold. So the first 2 ideas, resonance, we can talk very precisely to the atoms. Doppler versus Zeeman, we can talk to precise velocities, and we can choose the velocity by choosing the magnetic field. The last step is just let the hot atoms out. Okay? What I mean by that is something that we call evaporative cooling. So once we've got these atoms cooled down to 20 microkelvins, we can't get them any colder. That's where that laser that was cutting steel at the beginning comes in. If we focus that laser into the chamber, the atoms are drawn, again, very gently, given what it does to steel, they're drawn very gently to the focus. They want to go to the brightest part of the beam. And that makes a little trap that looks like this. And when you trap things quantum mechanically, you get specific energy levels. So that's what I'm drawing here. Specific energy levels in the trap, and we've got some atoms sort of scattered amongst them. And the key, this super complicated idea is turn the laser down a little. When you turn the laser power down, the trap isn't quite as deep. So the atoms at the top, these are the ones that had the most energy, they're not trapped anymore. They leave. Okay? When they leave, they take way more than their fair share of the energy with them, which is great, Now, once they're gone, the atoms are out of equilibrium. They'll have some collisions, they'll redistribute themselves. Maybe one grabs too much energy and rolls out. Awesome, take it. So by turning down the laser power, we end up with a gas that's much colder than before we turned it down. And so what do we do in the lab? Well, we just keep turning it down. We keep turning it down until we're about to run out of atoms, and we can get down to temperatures like 10 nanokelvins by doing that. Okay? So I hope that those 3 steps are fairly straightforward in your head now, right? Resonance, Doppler versus Zeeman, let the hot atoms out. Now, it turns out when you try to do this in the lab, it's slightly more complicated. Maybe much more complicated. So we need a lot of lasers, we need a lot of controls. At the end of the day, it's a whole lot of work just to implement those 3 ideas. But it's also a lot of fun. So that's it. That's how we get down to these temperatures that we want to work at when we want to look at ultracold chemistry, we want to look at the quantum behavior of many particle systems. Okay, so that's how we get ultracold. What do we do when we're there? On with the chemistry. You were promised chemistry. You were not promised a chemist, though. Perimeter Institute for Theoretical Physics, great. I'm on my home turf here. I do feel the need to make a disclaimer when I talk about chemistry, which is that I'm not a chemist. I'm going to talk to you about chemistry from a physicist's perspective. It's funny, the chemists don't laugh when they see that picture. They're like, yeah, that's right. Okay, so given that, this is my physicist picture of chemistry. Okay? We have reactants, that's what we start with. We have products, that's what we end with. All the good stuff happens in the middle. That's the dynamics that we want to understand. Okay? So in physics, we might call that scattering. It's a little reductive, but they come in, they bump into each other, stuff comes out. Okay? Now, given that, here is a molecular dynamics simulation of a very simple chemical reaction, the kind of chemical reactions we study. So the reactants are a diatomic molecule and a free atom. They come in, an awful lot of stuff happens, and then something else comes out. It's a different molecule. This one's red and green instead of blue and green. This one's spinning. That's fun. Okay? So some kind of reaction happened during all of that mess in the middle, and that's scattering. Easy. That's chemistry. Okay? Chemistry, real chemistry, more complicated than the story we're telling here. So this is a motor kinesin protein. It's carrying a vesicle down a microtubule, and this is happening inside your body as we speak. Okay? These little guys are carrying stuff where it needs to go in the cell. Kind of adorable, little clown shoes. So why on earth would we think that something as simple as 3 atoms banging into each other has any relation whatsoever to this kind of cool stuff that's going on inside your cells? The answer comes when you look closely at how this guy works. Right in, I don't want to be rude, but right in there, where the 2 legs come together, okay, there's a binding zone for ATP. When ATP binds in there, it dephosphorylates, which releases some energy, and it goes like that. That's it. That's the whole reaction. Okay? A little bit of energy, changes the conformation slightly, but it changes the conformation in the middle of this hinge that's got the big clown shoe on a rope, so it looks really exciting. But the actual chemical dynamics, the sort of complicated quantum mechanical things going on to make a reaction happen, it's very local. Okay? So these large-scale reactions, these behaviors, oftentimes they can be understood in terms of very simple local interactions. So our goal is to take the understanding of these simple local interactions to the nth degree and then be able to bring them back to sort of real chemistry. I was going to say I don't like that term, but it's fair. Okay. No one is looking to do chemistry at microkelvin temperatures and like build a factory. Right? We're here to learn the fundamental dynamics of these reactions so that we can then talk forward to people who are doing that kind of stuff. So one of the reasons we go to ultra-cold temperatures is chemistry actually gets more complicated as you get colder. Okay? So I showed you we want to think about a diatomic molecule and an atom. They're running into each other. That's our chemical reaction. if you simulate these reactions at 1,000 Kelvin, they're pretty boring, right? It just kind of, they come in, something bangs real hard, something shoots out, done. Okay? But as you start turning the temperature down, the dynamics at short range gets much more complicated. Okay? In fact, at some point, it gets so complicated that the simulation just doesn't end. Now, in a real reaction, it has to end at some point, but we run out of patience on the computer. Okay? So much is happening. This is, by the way, not like a censorship dot. This is actually just all three colors have happened in every single point, and so it looks gray. Okay? Our goal in these experiments essentially is to look behind the censorship dot. What's really happening in there? What can we learn that's generalizable about chemical reactions more broadly? And how can we use that in the future? So when we started these experiments, we started with a really simple question. Okay? Our experiments were done with sodium-lithium molecules. Okay? If you remember when I flashed by the pictures of the lab, there was that same orange that I had at the beginning for sodium. Turns out that sodium vapor lamp makes the same color as the lasers we use to control sodium atoms down to microkelvin temperatures. Okay? So we have sodium and lithium atoms. We make them both ultra-cold. We do some fancy dance with lasers and stick them together into molecules. Okay? And then we have a simple reaction. I want to take one sodium-lithium molecule, one sodium atom, have them react. And the question was, do they? Okay? Simple question. Do they react? There are three possible products of this reaction. Okay? Again, real chemistry, thousands of product states, all kinds of cool stuff happens. We bring it down to where there's three things that could happen. One is we get sodium-2. One is we get a different sodium-lithium, and one is we get a different sodium-2. Now, the difference is important, so let me get into this. These arrows are symbolizing the spins of electrons in these molecules. Okay? So in the sodium-lithium molecule, you have two unpaired electrons, okay? And their spins point together. Now, if the spins are opposite to each other, it turns out you can make a way more deeply bound molecule. Okay? The molecule we made, it has a binding energy of like 1,000 kelvins. Now that sounds like a lot, but this one has a binding energy of like 10,000 kelvins. Okay? So it's a much tighter bound molecule. So if we bump these into each other and a spin flips, we definitely have a chemical reaction. Huge amounts of energy released. Okay? Similarly, if a spin flips and the two sodium atoms end up stuck together, again, we have this very tightly bound molecule, 10,000-ish kelvins worth of energy released. On the other hand, if the spins don't flip, if somehow the spins all stay aligned, the only thing that could happen besides this is the two sodium atoms get together, and it turns out that two sodium atoms with their spins aligned in a molecule, that's actually higher energy than the one we started with. This is in wave numbers, which is an odd unit. It's about 75 kelvins of binding energy. Okay? We're working at 1 microkelvin. There is no way they run into each other with enough energy to produce that molecule. So energetically, these two at the bottom can definitely happen, okay? And the one at top can't. The question was, does it happen? Because it requires a spin to flip. Okay? It's a very simple question about chemical reaction. Can that spin flip during that chemical reaction? But it gets at the complexity of these dynamics, because flipping spins, sometimes it's hard. Okay? Turns out. So the question is, inside of this complicated dynamic, do we have the spin flip? Now, the answer that essentially every theorist would have given us, did give us, was, of course it will flip. Look at what's going on. You can't even see what's going on. They're together forever. There's so much happening. Anything that is allowed by symmetries, okay, symmetries do constrain reactions, but anything that's allowed by symmetry ought to happen. So we said, great, ought to. Let's find out if it does. So the first thing we did was we put these together, but we gave the sodium atom just a little bit of a tilt. Okay? Now, if you have gotten the drill at all about quantum mechanics, you can't actually do tiny things, right? Things are quantized. Well, everything's tiny in quantum mechanics, but you can't do arbitrarily tiny things. So when I want to tilt the spin of that sodium atom, my choices are straight up and about like that. I can't do anything in between. So I make the smallest tilt that quantum mechanics lets me make, and I look at the reaction. And you see how fast it is. Well, I picked the axes so it looks fast at least, right? It looks really fast. They're gone, 1/10 of the way across the screen. Must be fast. Then we said, okay, now make it point straight up. And what we see is there is still a chemical reaction. So what I'm plotting here is just how much of the reactant is left. Okay? We don't do products. We just watch the reactants go away. That's how we know a chemical reaction has happened. And what we see is that the reactants hang out a whole lot longer when that spin points straight up instead of as close to up as it can be without being all the way up. Okay? Do this quantitatively, it turns out that the reaction runs 80 times slower in this state versus that state. And in fact, that reaction is so slow, it's almost as slow as if you don't have sodium there at all. Okay? The molecules will naturally react with each other. We do things to slow that down. Can't stop it completely. So that little tiny change in the spin makes a huge difference in the reaction rate, and that was surprising. Okay? It was surprising, and I thought, surely that's useful. So I went to the chemist. I said, guys, check it out. I said, sodium what? Sodium-lithium? Is that a molecule? I said, come on, it took a lot of time to make this molecule. Yes, it's a molecule. Okay, it's a molecule, but it's not necessarily the kind they think about all the time. Okay? So I kept looking and thinking, this ability to control reactions with a small change in spin, that's got to be important somewhere. And it finally fell in my lap. It is important somewhere. It's probably important in lots of places, but I know at least one, which is the electrolysis of water to make hydrogen and oxygen. Okay? Now, when people talk about the green future, a green economy, you need a way to move energy around, and hydrogen is a great way to do it. Okay? So the ability to split water into hydrogen and oxygen is probably going to be quite key to the energy economy of the future. And it turns out it's a spin-dependent reaction. Okay? So this is real chemistry. I can't explain it all. But the important thing is spin. Yeah. No. So what happens is oxygen molecules have their spins aligned. The two spins from the two oxygen atoms are aligned, and that's really unusual for molecules. Not for the one we made, but for most molecules, that's unusual. And so it turns out when you split the water, if you split two water molecules and you get oxygens like that, they won't make an oxygen molecule. They actually make peroxide, which is no good for the places you do these reactions. There's a whole bunch of research now to figure out how to get them to come out spin polarized. And the answer is not, well, do it at a microkelvin, then you can control the spin easily. But what we're learning about the dynamics of spin polarized and spin unpolarized reactants is directly relevant to what they're doing. Okay? So it is a very peculiar place to do chemistry, but when we learn these sort of more basic principles, we do see ways to take them out into the world. So there's one really interesting thing that we brought out of this research. Well, more than one. I want to tell you about one. Which is the idea of a chemical resonance. Okay? So what we have here is essentially the reaction rate. Okay? It's the reaction rate for that sodium-lithium and sodium. Everybody spins pointing perfectly up at different magnetic fields. Okay? Now, we're changing magnetic fields, and it turns out we can change the reaction rate by a factor of like 300. In fact, like some very, very fundamental laws of quantum mechanics are the only reason this doesn't go bigger. Okay? So at least by a factor of 300, we can change this reaction rate just by tuning a magnetic field. Okay? Now, that also is surprising. That's also something that theorists steadfastly told us wouldn't happen in our system. So good, it did. I want to tell you why this happens. This gets at one of the key things about doing chemistry at ultracold temperatures, which is we have complete control of the reactants. Now, when you go to the chemical closet, you grab some sulfuric acid and some copper. I don't know why. You've got control of the reactants in the sense that you bought it, it has the right label. What you don't have control of is the quantum states of the reactants, right? If I have water in my reaction, is the water rotating? Are the little arms vibrating back and forth? Water can do that. Does it all the time, apparently. Not in our experiments, but all of these different things are happening simultaneously because you're at 300 Kelvin. Doesn't sound hot, maybe, but it's really hot compared to a microkelvin. So all of those different things are happening at once in that beaker. Somewhere in there is a really important reaction channel that passes through one specific state of the molecule, but you'll never see it because it's all happening at once. At ultra-cold temperatures, we produce the reactants, and we produce them in whatever quantum state we want, because after all that work that made that messy lab, the payoff is we can control the quantum states precisely. Okay? Here, we are looking at one very specific initial state for the reactants, and what's happening here is a purely quantum mechanical effect. There's interference going on within the molecular potential that produces a resonance. Okay? Take all those words. Those are good words. You can say them to someone later. They'll feel very proud. What do I mean by that? Okay. So I want to start with what to me is a very comfy model because I spend most of my time playing with lasers. That's not true. I spend most of my time writing grant proposals. I used to spend most of my time playing with lasers, and it was great. So when you're playing with lasers, one of the things you might do is point two mirrors at each other. Okay? Now, mirrors are reflective, so if you shine light on a mirror, it should bounce off. That's the goal of a mirror. Okay? But it turns out if you point two mirrors at each other, and you shine light that's at exactly the right frequency, it'll fit between the mirrors. You see? It's sort of 0 here and 0 here. And it fits a nice even number of waves between. If that happens, when it bounces, the little bit that leaks through, it bounces, it comes back, a little bit leaks out, and it turns out it interferes destructively with the reflection. That's a funny thing. But if these mirrors are exactly the right distance apart, instead of all of this incoming light bouncing off, it makes it into the cavity, it builds up a huge field inside of the cavity, and the same amount that was coming in leaks out the other side. Okay? So one mirror, highly reflective, two mirrors, usually highly reflective, but at just the right frequency, all the light passes through. And in the process, you build up a huge power inside the cavity. This is an effective interference. Now, it's interference with light, which you can usually describe in sort of classical terms, right? It's an electric field, if you know all this, right? The wave either has constructive or destructive interference. It turns out you can think of a molecular potential the same way. So a molecular potential, there's no axes on here. I would not let my students get away with this. This is energy and distance between two atoms. Okay? So if two atoms are far apart, they don't interact very much. The interaction energy is basically 0. As they roll together, that interaction gets much stronger very rapidly, and then suddenly it's like they run into a brick wall. Okay? That's when the charges are pushed so close together that the electrostatic forces just push everything apart. The input's a lot more gentle. And it turns out that that basically acts like two mirrors facing each other. Okay? Now, it's not two mirrors for light. It's two mirrors for wave function. Okay? The movements of atoms and molecules, particularly at ultra-cold temperatures, this becomes obvious. They move in a way that looks wavy. I don't want to say they're a wave, but their movement looks wavy. And the way we describe it is with a thing called a wave function. And if you've heard about wave functions before, then you've probably heard things like when you square the wave function, it tells you about the probability for finding a particle here, there, there. Okay? So that's the idea. The way that they move looks like a wave, and it tells you a probability distribution for where you may or may not find them. Okay? Now, why does it look like two mirrors? Well, this mirror is pretty clear. Okay? It's like a brick wall. Anything that gets in there bounces off of it. So if a wave wanders through this potential, gets all the way to this side, it will reflect. 100% probability. But this is funny. This is rolling downhill. This is one of the things that is surprising about the wave nature of particles in quantum mechanics. Okay? If you roll a bowling ball toward a cliff, you know very certainly it's going to fall off the cliff. Right? If you roll a quantum mechanical bowling ball towards a cliff, there's a 10% chance it bounces back at you. Okay? Now, that is peculiar. You have actually seen this yourself. Okay? If you look out a window at night and you see your own reflection, it's a very similar thing. right? That window's not a mirror. You look right through it during the day. It turns out there's a very small amount of light that's reflected at each surface. So when the environment for a wave changes, you get some amount of reflection. And it turns out for quantum mechanical particles that move in a wavy fashion, the same thing happens. So as this potential rolls downhill, it's like a gentle rolling, and the wave function will reflect on it. So normally, we see almost all the wave function reflect, and the wave function tells you about probability. So normally, there's almost no probability for the atoms to get close enough, or the atom and the molecule to get close enough to have a reaction. Okay? Now, to understand this, when we send in the wave function, we do have something like a Fabry-Perot cavity. We do have something like two mirrors, but it's dirty inside. Okay? So what actually happens is the wave that makes it through gets lost here. Okay? It gets lost to chemical reactions. Usually at ultra-cold temperatures, chemical reactions at short range proceed so rapidly, so violently, that nothing comes back. Okay? The thing that was special about sodium-lithium with all the spins perfectly aligned is basically you get the dirt out of the cavity. Okay? It slows down the reaction rates at short range so that now this wave function that's coming along, if it's got the right energy, it builds up a standing wave in the cavity. Okay? You build up a big amplitude. This is how much was coming in. There's way more inside the cavity than was coming in. Okay? Just like with the light. And all that wave function that's in the cavity, that's probability. You're much more likely to find the atom and molecule close together than far apart suddenly. But close together is where the chemical reactions happen. So it turns out that by aligning the spins, we slowed down the chemical reactions at short range. Okay? And normally, that would give you a picture like this. Hey, not much makes it in, not much of it reacts. That's why we saw that factor of 80 reduction in reaction rate. But if you use a magnetic field to tune the energy just right, that happens. Now you have a huge probability to be at short range, and even though the chemical reactions are slower at short range, you're so much more likely to be there that the reaction rate shoots up. Okay? So when we come back to this plot, the black dashed line, that's how fast we would lose them if everything that made it to short range was lost with 100% probability, which sounds like the fastest reactions you could have. The reason we can shoot way past that bound is we have less reaction at short range. Counterintuitive. Less reaction at short range gives us a good resonator. It allows us to pull probability into short range where it normally wouldn't get, and then the reactions take it away. Okay? So resonances of one kind are how we scatter light off of the atoms. A very different resonance of a very different wave is why we get chemical reactions to run faster than you would have thought was possible based on sort of just normal stuff gets together, it reacts, and it's gone. Now, I wish I could tell you a whole bunch of other stories. Turns out we found lots of these chemical resonances. We found them in different states. Turns out that wasn't the only state that turns off the reactions to an extent that you can see these resonances. And by studying the distributions of these resonances, we were able to learn very fundamental things about the dynamics at short range during the chemical reaction. Okay? Things that we're still trying to fully understand because every time we talked to theorists, they were like, well, that won't happen. And then we made it happen. Okay? Not because we were good, just nature happened to work that way. Okay? So with that, I want to tell you that's the team that made this happen. And they've all graduated, gone on to glorious things, making far more money than me. And so now at Waterloo, we're working on the next generation of these experiments. Okay? So we're working on building a cesium-lithium experiment. Now, lithium is still there. Cesium's a new atom. Turns out by changing one atom in the molecule, and that particular atom is important, we will be able to learn new things about the reaction mechanisms that we couldn't have learned by just looking at one. Okay? So that's the goal. Everyone's looking off to a bright future, or whatever the photographer told us to look at. I want to give you just a taste of what we're doing now, because We're still in the process of building the lab, but we're trying already to understand those dynamics. The short-range dynamics that still sort of bedevil us. You just can't calculate it in a fully quantum mechanical way. So we want to try to understand, are there rules of thumb, are there heuristics? Can we have some intuition about how this happens? Part of that is some work that one of my students is doing right now, doing numerical simulations, kind of similar to the ones that produced the pictures I was showing you earlier. These are fun. It turns out that in the process of these ultra-cold chemical reactions, very, very chaotic dynamics ensue. Okay? For the moment, that looks like it's got 6 petals, but that'll be gone. Okay? Everything gets mixed up. Everything ends up going sort of everywhere it could. That's the basic idea behind all of these comments from theorists that, well, yeah, of course it'll happen. Everything can happen. Okay? Well, we're trying to understand exactly how everything is the everything that can happen. And we found something interesting. If you run this for a really long time, you get a picture like that. And it's just covered, right? Everything everywhere. But turns out if you look a little more closely, which my slides may or may not let me do. Here you go. Not quite everything happened. Turns out some of the symmetries that are required to make a classical simulation look like a quantum mechanical simulation squeeze the dynamics into 2D. That was not what we expected. Still trying to understand exactly how this pays off in the quantum mechanical context, but it's giving us a hint that there is something more than just everything is allowed, so everything happens. And since I have 2 more minutes, I'll just mention that sometimes I'm an economist. No, not really. Sometimes I collaborate with an economist. So almost everything that I'm doing is looking at collections of quantum mechanical particles and asking what happens when we put a bunch of them together, we get them to interact strongly. All of our theories are too complicated to solve with pencil and paper, and frankly, they're too complicated for computers to handle. Okay? That's where I want to be. I want to be in the place that we can't calculate anything and learn what's going on. Turns out you don't need quantum mechanical particles to come up with things you can't understand. So in my lab, we're also working on models of humans using statistical mechanics. To do that, we basically define a human, no, we call it an agent, some little thing that follows some very simple rules. At the moment, we've mostly been looking at models of housing segregation because they turn out to have sort of very simple rules, but very complicated emergent states. And what we're interested in is, what is the emergent behavior that you see in large groups interacting under simple rules? Now, part of the interest here is just, that's interesting stuff. Part of the interest is if we look back at quantum mechanics and we say, what happens when I put 10,000 particles together and they do something really complicated? One question is, well, what part of that is quantum mechanical? If we study the behavior of classical particles, people, interacting through some simple rules and how complex behaviors emerge there, then we can look back at the quantum mechanical situation and say, aha, so that's what was fundamentally quantum mechanical. Some of this is just about the emergence of complexity through interacting systems, and some of it is about the fact that those systems happen to be quantum mechanical. And along the way, we get to talk to people like the Bank of Canada, who definitely wouldn't have taken my calls 2 years ago, and we see that very small changes in the rules for the dynamics of these agents, these people, lead to wildly different outcomes in the long run. Okay? So we're just digging into this, writing up a paper at the moment. The idea is to say, we've spent so much time thinking about complexity in the quantum mechanical world. If we take some of that lens and turn it back to the classical world, what more can we learn there? And with that, I thank you for being here, and I'm happy to take questions.